That'll help you. So first thing, I'm gonna go to my apps and I'm going to run Xming. Come down here to Xming. And so then we run that. And eventually down here, you see this little X thing show up. And after it sort of initializes itself and dusts itself off and gets ready, you won't see that anymore. You'll have to click on the show hidden icons thing to see it in here after. See there, it disappeared. So that's how you'll know if the X Windows server is actually running there in the background. It's up in these hidden icons. So he's running now. So now I want to go do our putty thing. So there you go up there and run putty. And it doesn't matter which one of these we pick. There's just a bunch of them in there. Oh, let's go with 10 this morning. What the hell? So we load it up and notice that in here in the X11 thing, we've got the X, X Windows forwarding thing going on, right? So we open that up. You can set it up where it already knows the login name you want to use as part of the session, so you don't have to type that over and over again. And so we log in, and so now we're on the Linux 10 machine. A couple other folks out there, and we want to go over to Schofield now. All right. So rather than having to type this big, long SSH blah 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 thing in every time, I just made myself a little shell file in my um, bin directory here called toschofield.shell and script, and it just contains this one line, so I can just type to Schofield instead of having to type all this junk all the time. And that's in my bin directory. And the bin it's a Unix kind of tradition. Stands for binaries or executables, in other words. Um, and so that's a sort of common standard thing that everybody pretty much uses is under your home directory, you create a bin directory like there, right? And then you arrange to have that bin directory show up as the first thing on your path, right? So you see this home Meehan bin thing is the first thing in the path. So whatever command I type in here is going to go hunting down this series of directories looking for a file with that name. And so he's going to hit this bin thing in my home directory first. So you just use that to squirrel away all the little shell scripts or commands that you want to have that sort of take precedence over the normal sort of stuff, right? So that's why when I type in to Schofield, um, it's going to find that in the bin thing and then run it. And it's just going to do that SSH thing. So my Schofield password, which is different, of course. And now I'm on Schofield. So you notice that we did the -y thing, wherever the hell that went, um, when we logged into Schofield. So we've got our X Windows stuff all hooked up like elephants, trunk to tail, in a line. You got to have the unbroken chain, right? We did the putty thing. It had the exporting when we went to the Linux 10 machine. We went from the Linux 10 machine to Schofield. We got the exporting going. So you have to have all of them lined up with the exporting going on. You can't break the chain or it won't get back to you. You won't see your X Windows stuff. So now we can do things on Schofield. Um, CD always takes you back to your home directory, and then I'll go to 247, and then we'll go to like sample programs, and there ought to be a sample program in there called tests something. So Emacs, I use the tab, for the file name completion, so I don't have to type the whole thing out. So we'll just run Emacs over there on Schofield, and the X Windows junk will get forwarded back over to the Linux 10 machine, which will forward them down to my machine here. And we'll see the window getting rendered here on my machine. And to get it cranked up, there's maybe a slight delay or whatever, but once you get it going, it's pretty quick. So we'll resize this sucker. And so now we have Emacs running over on Schofield. We see it on our computer here, and we have this file that lives over on Schofield that we're editing. So we're sitting in our house at home, and we're running an editor on Schofield, and we're editing a file over there that's going to live in the file space over on Schofield. No muss, no fuss, right? So we'll get back to that later. But in fact, my office hours today, since it's Wednesday, are at 1 to 2, not the normal 2 to 3 times like they are on Monday, Thursdays, and Fridays, because on Wednesdays I have a research group meeting at 2:30, so their office hours are 1 to 2 today. And if you show up, just follow the link for Wednesday office hours out of the Canvas pages. If you show up at the office hours today, I will give a little workshop, unless people have other things they need to ask about. But I'll give a little workshop on some of the wonders of how to use Emacs. So there's a collection of knowledge about Unix and the standard tools that we have in the Unix environment that all the true geeks know, right? And so you're just going to have to learn, and it's going to take years and years to accumulate it all. But you're going to have to learn all this sort of inside secret handshake kind of secret knowledge that all the real computer geeks know, right? And so a lot of those things are how to do things in the shell in Unix and make it jump through fiery hoops with single commands, things that you can type in 15 characters on the command line that if you did click and drool GUI interfaces would take you 3 days to accomplish, right? So true computer geeks have this big body of knowledge about all these little magic things you can do in Unix and the standard Unix utilities like Emacs or whatever. And it'll make your life a lot easier once you learn those, and you'll get your wizard hat fitted and you'll be able to make fire jump from your fingertips, right? So it's just going to be a process of over a period of a long number of years to accumulate all that. But hopefully in this class, you'll be beginning to get a little of the beginnings of that, a little familiarity with how we do certain things in the Unix world and how we use the certain tools. So if you show up at the office hours today at 1, I'll give you a little tour of some of the magic that you can do in Emacs. Okay. So we've got this Emacs running here, right? And you'll notice over in the shell, he's not giving us our prompt back, right? So when we type that command in, he ran that thing. And since we have the X window stuff going, he put it in another window. If we didn't have the X window stuff going, he'd have a version of it running right here in this terminal window. By the way, there is a difference between the terminal and the bash shell. The bash shell is running inside of the terminal window interface. So Point is, what if I wanted to do something over here in my shell, type some other shell commands in or do something, but he's not, giving me my prompt back. So this is what we call running in the foreground in Unix, right? And if I'd put an ampersand at the end of that command, he would have kicked Emacs off in quote the background or detached over here running, and then he would have given me my shell prompt back. But I didn't do that. I go, oh well, shoot. What if I want to do some commands over here? Well, all is not lost. Here's the magic trick you have to know. You come back over to your shell and you type Control Z. Now, Control Z takes that thing that was running that he was waiting for to terminate and kind of puts it on ice, just stops it and throws it in the background there, right? And if you type jobs, you'll see all these jobs and what state they're in that you've kicked off. So if I want to get that Emacs thing cranked back up, I can just type BG for background, and it'll take that last guy that I dumped in there and it'll throw it in the background. So you see, tack the little ampersand on. It's just like I had originally put the ampersand on there. So now this guy over here is running and I can interact with it. And now I've got my shell prompt back, right? So if you ever get in a situation where you've kicked something off and you go, oh crap, I need to do something in the shell over here, just Control Z, BG, and then you're back and you can do all your shell commands, right? Is everybody okay with that? Questions? One of 8 million little things about using Unix and the shells you have to learn. All right. So we'll come back to this hopefully later in this lecture. We may or may not get to it, but the little program and what it does and how it does it. So we're going to get into the lecture. So any questions about what I did to kick off Xming and how to kick off, Putty and then go from the place over to Schofield, run a program over there? You getting kind of familiar with all this junk now? Okay. No questions? All right. So let's get into the lecture. So here's our lecture for the day. And these, of course, are all out on the, excuse me, these are all out on the Canvas pages with mysterious names like Lecture 2 and things like that. So we want to start learning about how data is represented in the computer. What does it look like laying in the memory of the computer? How does an integer get represented? How does a floating point number get represented? What do they look like? What are the bit patterns? How does all that work? So that's what this business is about: bits, bytes, and integers. We're going to learn about bit level manipulation, how we manipulate things at a bit level, and then when we're screwing around with adding numbers and doing things, what are multiplying them, what's all that look like, and what are the considerations we need to understand about it. So to get going, you go back down to the very bottom level. Of course, everything in the computer is stored in binary. That's why we call them digital computers. That doesn't make sense, does it? Right? They should be called binary computers. Digital's base 10, but that's what they call it, digital computer. So anyway, the stuff is ultimately sitting in a device, right? And everything is represented as a 0 or a 1 in all of the encodings. They're all encoded in binary. And what that boils down to physically, electronically, is that we just have two voltage levels. And if it's in this range, we call it a 0. And if it's in this range, we call it a 1. Now, these actual voltages differ depending upon what type of circuitry, whether it's CMOS or TTL or whatever. These will be different, but the idea is the same. You have a range here and a range up here, 0 and a 1, and then there's this transition phase that goes from one to the other, and that's the transition. It's like no man's land, it's like unstable. It's not in any state when it's transitioning. So there's a little bit of that going on. Excuse me. So then we look at all these bits that are zeros or ones sitting in the memory of the computer, and we want to not deal with individual bits. We want to deal with them in chunks, right? So the chunks that we like to deal with are called bytes. 8 bits is a byte. And does anybody know what the name of the chunk for 4 bits is? Anybody? No? Yes. It's called a nibble because it's byte, nibble. We have to amuse ourselves, right? So, excuse me, get a little hoarse this morning. So if I had 8 bits, and that's two here, means this is binary, right? So here's my 8 bits. The lowest value I could store in 8 bits would make them all zeros. The largest value I could store in 8 bits would be to make them all one. So if I have all zeros, this is a 4 bits, a nibble, right? And I had all zeros in decimal, that would be, well, believe it or not, zero. And in hexadecimal, base 16, it would be zero. Now, decimal, which is what they taught us in whatever it was, the first grade or whatever, has 10 symbols. That's why it's called decimal, right? And those symbols are the symbols 0 to 9. But when we go to hexadecimal, base 16, not base 10, we need 16 different symbols to represent one position. So we just use the letters A to F for the additional 6 symbols that we need. So if you're thinking in terms of decimal, the A in hexadecimal is a 10, the B is an 11, C is a 12, F is a 15, right? The biggest thing you can have in one position in base 16 would be a 15. Biggest thing you can have in one position in decimal would be a 9. So what the heck is all this hexadecimal stuff about? Well, turns out if you write down one hexadecimal digit, that takes 4 bits, right? Because you can represent the values from 0 to 15, 0 to 15, 0 to F, the 16 symbols that we have, right? So when we write a bunch of binary, want to look at a bunch of binary stuff laying in the memory of the computer, we don't want to blow our eyes away with like 8 billion zeros or ones. So we write it in hexadecimal with each hexadecimal digit, which really isn't accurate use of the word digit, but in each position, hexadecimal position represents 4 binary bits, right? Any questions about that? So that's the only reason we bring this hexadecimal stuff up. It's just a shorthand way of writing a big long bunch of binary junk and not having so many things to deal with. We just group them in groups of 4 and put a hex digit in there, right? So in C, you can write down a number in a C program and say, oh, this is a hexadecimal number, base 16, not base 10. And the way you indicate that in C is you put this little 0x thing in front of the number, and then the compiler goes, oh, you're giving me a hexadecimal number there. Makes no difference whether you use the capital letters or the lowercase letters, right? So when you see that written down, that'll mean, oh, this guy's talking about a hexadecimal number. We just use the sort of C style notation so we know what we're expressing when we write these things down. Everybody cool? Anything about this? Go next slide. All right. Now you can either use the raise your hand thing, you can type on the chat, or you can just chime in, on your mic, however, whatever works for you. So now we talk about byte oriented memory organization. The memory of the computer, you can think of the physical memory of the computer, like this particular computer here has 12 gigabytes of DRAM in it, the big physical memory on the computer. You can think of as just a big, long linear array of bytes, right? And the Intel processor assigns an address for each of those bytes. So the first byte is address 0, the second byte is address 1, the third byte is address 2, on and on and on and on and on, right? And we call that a byte addressable computer. There are computers like old IBM mainframes and things like that where the addresses represent words. And so, like on a IBM mainframe, a 32-bit word computer, the first address points at 4 bytes. The next address points at the next 4 bytes. That's a word addressable computer. The Intel computers are all byte addressable, where you can point the address at any individual byte in memory. So you think of the memory when your program is running, your program is actually not generating those physical byte addresses of all the memory in the computer. It's actually generating what are called virtual addresses. And in this course, one of the really great things that you will learn, that sort of the secret knowledge that brings you into the geek community, is you will understand how that actually happens and how that works, and physically what's going on the computer, how the virtual address is translated into a real address, and how all the hardware functions to accomplish that. So the program, when a program is running, your process, a program in execution is a process, right? So when your process is running on the computer, it generates references to virtual addresses. And the size of that virtual address space depends on what flavor of computer you're on. If it's a 32-bit computer, you'd have a 32-bit virtual address. A 64-bit computer like this Core i7 laptop that I'm playing with here has a 64-bit virtual address. So we'll get really gory detail, more than you ever wanted, about how all this virtual address business gets translated onto the actual physical addresses in the machine. So machines have word sizes, even byte addressable machines. And the word size basically amounts to what is the size of the registers that live up in the CPU. Now, the only thing memory does is you pull something out of memory and you push it back into something back into memory. You can't manipulate the data when it's laying in the memory. Caveat, that's not strictly true of all computers. There are some computers that have opcodes that pull something in and then manipulate it and stick it back in one sort of atomic thing. The Intel computers don't work like that. To manipulate anything, you have to suck it up out of the memory into a register in the CPU, and then you can like suck up two things into two different registers, and then you multiply them together and get a result and cram that back into memory or whatever. So you bring everything up into these registers in the CPU in order to play with it, manipulate it, right? So the width of those registers is really what we mean by the word size of the machine. 32-bit machine means it has 32-bit, registers. 64-bit machine has 64-bit registers. The address size, since we hold the address that we're referencing in certain register, is also involved in this word size. And this is an old slide. Most current machines don't use 32 bits. They're all 64-bit, have been for years, right? But if you had a 32-bit address, and we're talking about generating a physical address now, the most memory you could put on that computer would be 4 gigabytes, right? Because that would be how much you could address in 32 bits. A 64-bit address, you could address an awful lot more, but the 64-bit virtual address that we generate, we really don't use all of those bits will be translated to a physical address. We only really use 48 of them, right? So while we think of having this 64-bit virtual address space, when it turns into a physical address, I mean, when it turns into even the virtual address, this is not the physical address. That's 52. But anyway, when we on our 64-bit machines, we're really not using the high 16 bits. They're all zeros. So we're really only using 48 of them, but don't feel too slighted because 48 bits of a virtual address space gives you 256 terabytes per process, right, of virtual address space. We'll see how all this fits together in the hardware in gory detail later. Okay. Now, the opcodes on the computer are designed to manipulate a whole range of sizes of things. They can manipulate things at byte at a time. They can manipulate them 16 bits at a time, 32, whatever. So that leads to this concept of data types. What you see here is the data type names that you use in a C program when you're declaring a variable. It's of this type. And it basically is saying, well, how big is it and what do you intend on doing with it, pretty much, right? And like all things in a computer, everything is pretty much a power of two, right? So you see that 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Don't pay any attention to this man behind the curtain here. We'll worry about that later. But the sizes of these C data types, a character is a 1 byte entity. And he's showing you on a typical 32-bit computer, on the actual Intel 32-bit computers, and on the Intel 64-bit computers, what is the size that you get if you're writing a C program and you write some variable is of type char. How big is that when you're manipulating it? Well, it's 1 byte on anything, right? A character. Now, you've probably heard about these funky Unicode character sets that have multi-byte characters and all that. Don't worry about that for now. In here, think of everything as the ASCII characters, the 8-bit character codes. So a char is a 1 byte entity. A short stands for short integer, right? Which is 2 bytes. An int is an integer, is 4 bytes or 32 bits. A long depends on which computer you're compiling your program onto. This one is different, right? All those other ones are the same. There's only two that are different. Well, three actually, if you include pointers. The long on a 32-bit machine and you compiled your C program, you'd be grabbing things in chunks of 4 bytes. A long type on the 64-bit is an actual bigger than a int. He's twice as big. So you kind of get cheated on the 32-bit. If you said long in your C program, you still didn't get anything bigger than an integer. To get something bigger, you had to sort of say, long, damn it, or long, long, right? And actually give me an 8 byte thing on the 32-bit machine. So that's just a little strange, but that's just the way it is. So why do we really care about all this? Well, what if I wrote a program and I compiled it and I ran it on my 32-bit computer and it, worked okay or whatever. And then I take it and drag it over here to this other computer and I recompile it and I want to run it on that other computer. I want to port the program to a different architecture. Well, all of these longs that I was using over here were 4 bytes and all of them over here are 8 bytes. So issues that come up like overflow, values out of range, and all that kind of stuff are going to work slightly differently here than they would work over there. So it matters in porting these things around to know what size data you're actually dealing with, right? So the long is the same on all of them. The floats are 4 bytes. This is a 3.14, that kind of thing, floating point number. This is a double precision floating point is what that means. And it's twice as big, twice as big, twice as big. And once again, the long double, just like long up here, is the one where it's going to be different. Typical computer would use 8 bytes for that. The screwy Intel thing has this internal extended precision format that we'll go into detail later. And this Intel has a very long and tortured history. It's kind of like the family secret dirty laundry being aired in public, their relationship with how their floating point stuff worked and evolved over the years. So we'll see why this crazy thing is listed as 10 or 12, depending upon what phase the moon is in, or on the 64-bit machine, 10 or 16. That's this screwy Intel internal format. Truth be known, when you take a long double and you store it back into memory, is actually only storing 8 bytes. But the internal computation up in the CPU is happening at a extended precision. So don't worry so much about that. We'll talk about that later. Now, a pointer is an address, right? That's all we mean by pointer. And so on a 32-bit machine, an address would be 32 bits, 4 bytes. On a 64-bit machine, an address, something pointing at memory, would be 8 bytes. So questions about this table. You'll have this memorized completely in your head, and it'll be just like knowing the multiplication tables, right? These are 32 bits, these are 64 bits. The only place they differ is where? The long and the long double, right? Okay. We will discuss how everything works on both 32-bit Intel processors and 64-bit Intel processors. You'll learn both because, believe it or not, even on the 64-bit machines like this one, a lot of the software you're running on it is old 32-bit code that isn't really taking advantage of the fact that it's a 64-bit machine. So you need to know how that operates and what it looks like. This is the table right here. This is the standard 64-bit table, right? Except for that internal Intel weirdness, right? A 32-bit PC would be like, the old Pentium processors and those kind of machines, right? Um, yeah. So the more recent Intel processors are the 64-bit guys. Okay. Now, a register is just a chunk of space to hold something up in the CPU. We have a whole bunch of different registers, and you'll learn their names. They have weird names in the Intel world, like EAX and EBX, and then some of them have just generic names like R15, register 15. So you'll learn what all these registers are and how they get used by the operation codes on the machine. So if I have something sitting in a register and I want to put it into memory, there's 2 ways I could do that. Think in your mind's eye of, say, a 32-bit computer, right? With a 32-bit register that holds 4 bytes, right? So envision those 4 bytes sitting there and envision the byte on the right, call that byte 0, and then move to the left, call that byte 1, move to the left, byte 2, and byte 3. So I got these 4 bytes, byte 0 through byte 3, sitting in that register, and now I want to shove it into memory at some addresses. Well, there's 2 ways I could do it. I could take the rightmost byte, the byte 0 guy, And I could put him at the low address and then go to the left and byte one, put it at the next higher address. Or I could start at the left and take the byte three and put it at the low address and then move to the right and take byte two and put it at the next higher address. It's completely arbitrary how I design my computer, whether um, I start at the left and go from low addresses to high, or I start at the right and go from low addresses to high, right? Okay. So we have to have names for these and say, how does your computer work? So if I look at these processors, the Sun Spark processor, the Power PC that the old Macs used, which they don't use anymore, or how the bytes are laying in a packet that gets propagated across the internet, those are all using what we call big endian, where the least significant byte, the one in your mind's eye that you're thinking about, byte zero on the right, goes at the high address, and the one on the left goes at the low address. That's a big endian scheme. The Intel processors are all little endian, right? Little endian takes the least significant byte, the one you're thinking about saying on the right in your register, byte zero, puts that at the lowest address, then moves to the one on the left of it, puts that at the next higher address, right? So if you look at it, and we had this hexadecimal number, right? That's what the 0x means, right? This is a hex number. And I had a 4 byte 32-bit register on my computer, and I had that hexadecimal number sitting in it, which would be 32 bits, right? Each hex digit is 4 bytes, so 8 of them is 32 bits. And I want to take that register and I want to stuff it into the memory of the computer. Well, Big Endian would take the least significant byte, this 67 there, right? And it would put it at the high address. The most significant byte would go down at the low address. If it was a little endian computer, right, it would take the least significant byte and put it at the low address and then go to the next byte and put it at the next higher address. It's completely arbitrary which way you design your computer to do it. It doesn't really make any difference. One is just as good as the other, but different computers do it a different way. So you have to know that the Intel computers that we're going to be playing with here are what are called little endian computers. Now, does anybody know why we use this word little endian with an E? Does anybody know where that comes from? Somebody raise their hand. Nobody raised their hand. So, have you ever heard of the book Gulliver's Travels? Yeah. Gulliver's Travels is a book written by an Irish monk, and it's about this guy named Gulliver, and he goes to all these sort of fantasy lands from one place to the other and encounters all sorts of things as in his travels, and that's what the book is about. And essentially, what the book is a vehicle for satire, poking fun at the British government because being an Irish monk, there's a long standing tradition of poking fun at the British. And so the book has Gulliver go to these various places. And one of the places he goes to, these two political parties live there, and they have this one issue that they argue about endlessly. And they even come to fight wars over this issue. And the issue is if I had an egg, like if I made myself a soft boiled egg or whatever, and I wanted to crack into it, stick my spoon in there and eat it, should I open it up on the end of the egg that's the pointy end, the little end, or should I open it up on the end of the egg that's the big end? And this is their political issue that they argue on endlessly forever. And so obviously the one political camp believes that you should do it on the pointy end. They're the little Indians. And the other believes you should do it on the big end, and they're the big Indians. And that's where this comes from, since it's completely arbitrary. We have to have a name for it and how you design the computer. So we take this from Gulliver's Travels of the big Indians versus the little Indians or whatever. Now, it's easy to remember that the Intel processors are little Indian, right? Because the L's, right? The little Indian takes the least significant byte and puts it at the lowest address. So now you can never forget that, right? You take your least significant byte, goes at the low address, and then you mark your cross. So, why do I particularly care about whether my computer is little Indian or big Indian? Well, here is a dump of a program laying in the memory of the computer with what we call a disassembly over here. These represent the addresses in memory where these things are sitting. And all the stuff laying in memory, of course, is just a bunch of binary stuff, right? And we write it down as hexadecimal numbers. And what it means is these are instructions to be executed by the computer. And this is the assembly language instruction. Pop the EBX register, add this constant to the EBX register, compare long word 0 with, excuse me, 28 past where the EBX register points in memory. You'll learn all this assembly language stuff later. But the assembly language is just mnemonics for humans to read in the computer as it's executing it. And of course, pop the EBX register is this 5B means to the computer, pop the EBX register off the stack, right? So if I'm looking at a dump of the memory at this address, whatever, with all these things laying in it, and the disassembly, you see this constant, the dollar means constant in assembly language. I want to add, it's called immediate address, immediate mode. Take the constant, hexadecimal constant 12AB, 32 bits, right? 16 bits, four things, and add it to the EBX register. So what does that look like laying in the memory? Well, the least significant byte, the AB, is sitting here at this address, and the next higher address is where the 1, 2 is sitting. So knowing that it's a little Indian machine, this makes sense to me, right? This AB12 is this 12AB constant being added to that, as it's stored in the memory with the least significant byte at the lowest address. So you need to know whether you're looking at a little Indian computer or a big Indian computer. So when you're looking at these things laying in the memory, you can interpret them properly, right? It's a constant 12AB stored in little Indian form in the computer. Everybody okay with this? So we'll be looking at a lot of this kind of junk, right? The assembly language instructions laying in the memory of the computer. When you go into the GDB debugger, you'll be looking at stuff like this, right? Oh, here's the stuff laying in the memory, and the debugger is going to say, oh, I'm disassembling it for you, showing you what these opcodes mean, right? Any questions? Move on. Okay. Yes, Connor, you got a question?
Yeah, can you hear me?
A little louder, please.
Uh, is this okay? Can you hear me now?
That's good. That's good.
So is there any? Someone asked in chat, and I was also wondering: is there any computational difference between little endian and big endian? Because it doesn't seem like there is.
What do you mean by
Like
computation?
if you were to like try to process bytes or information in big endian, I think that's what the person was asking. Compared to little endian, would there be any difference at the end? Like, would one be slower than the other?
It wouldn't be a question of speed,
Or
but
I think that's what the or like op would one be not faster, I mean more optimal.
no, it's completely arbitrary decision as to whether you store it one way or the other. It doesn't
Okay.
make your computer run any faster or slower to do it one way versus the other.
Um okay,
It's
so
just that
then
if I want to look into if I'm writing a program and the program is looking in the memory on the computer and munching a bunch of data, I need to know how it's laid out in the memory, right?
yeah, yeah. So if little endian or whichever one existed before, why did they decide to go with a different way of reading it, I guess? Like why do both little endian and big endian exist if they do the
It,
same thing?
it's a completely arbitrary design decision.
Oh,
Yeah.
all right, that was it.
A historical note, though, when we invented the networking and the internet and all that, we had to come up with a standard way that when you shove the packets down the wire and you have like a number, an integer or something in that packet, do you put the integer in little Indian or big Indian, right? As it's existing moving across the wire. Well, the biggest dog on the planet at the time they were inventing all this was the IBM mainframe, which was a big Indian computer. And so the decision was made to lay out the stuff in the packets that go across on the internet. They're all laid out in big Indian form. But now, what's the most dominant processor on the planet? Well, it's the Intel processor. So it's little Indian. So there's code running constantly on all these computers that are pulling a packet in off the internet, taking that big Indian thing and flipping it around backwards so that now it looks like the right order to shove it up in a register on the Intel computer. So we're doing all that because they made the opposite decision of what would have been the most effective decision, because back then the mainframe was the dominant computer. Now the dominant computer is a little Indian computer. So there's a lot of flipping these things back and forth constantly with all this stuff going across the network that wouldn't have had to be done if they'd, made the other decision. Anyways, so I want to mention before I forget that if you come to my office hours today, which are immediately following this class, I think they're from, no, they're not immediately following this class. They're from 1 to 2 on Wednesdays, not 2 to 3 like the other days. If you come to my office hours today at 1, which you do by going to the link, over there on the Canvas page, um, I will give a little short, brief introduction to Emacs and how to do certain things in Emacs. Part of fitting your wizard's hat to be a true computer geek and know all the secret handshakes and inside information that all real computer geeks know is you have to learn a lot of stuff about Unix. You have to learn a lot of stuff about the standard tools that we use in Unix. And so uh, Emacs is an editor, but it's also uh, so highly prized by a lot of computer geeks that it's sort of a way of life, actually, right? Or a religion. So I will begin to show you some of the magic that you can do in Emacs to kind of get you feeling a little more comfortable about how you can just go over to Schofield here and pop this up. and edit a file, write your C programs, shove them in there, compile them over on Schofield. And so just to sort of out of band, away from class and away from the usual labs or whatever, if you want to know some of the beginning magic, and I mean, it will take you literally years to learn um, even, a large fraction of the magic tricks you can do with your fingers and feeding this thing commands to do things to the text. Um, but if you want a brief introduction to how this thing works and learn about some of the secret inside handshakes about that body of geek knowledge that you need to accumulate, show up at the office hours at 1 today, and I'll kind of walk you through some live sessions where you can get on Schofield and run it and follow me along, and you can show me your screen, I'll show you mine. We can, just have a little workshop on getting feeling comfortable with Emacs, because it's very convenient just to sit in your house and have this little window that's manipulating the data over on Schofield using this simple little tool. And I'll show you how to, little intro to that. So is there any questions about this business of the size, word size of computers, write these C data types down? What are you actually getting on the computer? How is it stored in the memory with the little Indian, big Indian business? Parker.
Can you hear me?
Yeah.
Okay, I just had a quick question. What's the difference between a physical address and a virtual address?
Okay, when your process is executing on a virtual memory computer, not all computers are virtual memory. The little computer inside your engine in your car doesn't use virtual memory, right? So the process running on this computer right here, when it generates an address, it generates a virtual address, which is a make believe or virtual memory space, right? And that memory space is humongous. It's many, many, many orders of magnitude bigger than all the physical memory I have on the computer. And each process thinks it gets this humongous virtual address space to play in, right? And what we do is we translate the virtual address into a actual physical address and then access the physical memory to get what you're trying to get, or where you're trying to store something or whatever. So the process is run in this make believe virtual address space that then gets mapped onto the actual physical addresses of the computer. And we will learn in gory detail all the stuff that happens in the hardware to make that magic trick happen, right? But it gives us the ability to have these processes running, thinking they have this monstrously huge address space to play in, but they don't really. We just have this little small chunk of physical memory. So we'll learn how all that works. Does that make any sense?
Yeah, that sounds good. Thank you.
It is one of the really, truly wonderful magic tricks that we do on modern computers, this virtual address concept. It's a really it solves an incredible number of problems with one solution, as we'll learn later, and how we implement the operating system, how we uh, share memory between processes. And there's all sorts of things that this one concept solves for us in very elegant, simple way. And it's, without it, things would look really, really different in terms of having all these bazillions of processes running and thinking that they have all this big, huge space to play in. So we'll learn gory details about it later or whatever. So if there are no other questions, then maybe I'll see you at 1 today just come and join the session, and we'll have a little workshop, and I'll teach you how to operate this magic trick, this magic piece of software here that can do incredible stuff, jump through fiery hoops, and make your life easy with a few little commands you can learn to manipulate the text and compile your programs without, you can compile, debug, edit everything right out of this editor without ever leaving the editor. You can run shell commands and get their output right out of the editor. You can go browse the internet right out of this editor. You can pop open a calendar. So it's got all this magic it can do. And I'll give you a short little introduction to getting you down the road of how to learn what to do in this editor. Okay. Questions? All right. Have a good one. After today, everybody will have been through the first lab. So I'll be putting the finishing details on next week's lab and get it out there. I'm still kind of refining it a little. There's one that you can see, but I'll put a revised version of it out there. And next week's lab, we'll be doing a little beginning C programming kind of stuff and actually writing some little C code stuff and running it and getting down the road a little bit on that skill that we need. See you later, guys. See you tomorrow. Okay. See you then.